Okay, the purpose of this podcast is to look closely at the vector equation of a line, how one actually develops that, and extend that into intersections of lines in 2- and 3-dimensional space from a vector point of view. So the salient points highlighted for this podcast will be the determination of the vector equation of a line to bring some meaning to this r is equal to a plus tb structure here. The angle between two lines we'll do briefly as a follow-up to a previous podcast about the angle between two vectors, and finding the point of intersection of two lines in 2- and 3-dimensional space. And we'll look once again more closely at the angle between lines as it relates to that scalar stroke dot product we saw between vectors in the previous podcast. So to jump into the beginnings of the vector equation of a line, if you thought and think about just a line as we've come to know it, let's say in 2-dimensional space, if we come over 3 and up 4 and have some point on the line and end up knowing something about the slope of that line, we're good to go with being able to construct a y equals mx plus c form of a line in more the Cartesian plane. But when it comes to vectors, what we're going to see is that we need, once again, a point on the line that's going to allow us to get from the origin up onto the line. And then there's going to be some vector designated as b, which will be some vector sort of free-floating in space that's perfectly parallel to the line in question, because that's going to help us move back and forth. So the theory looks something like the beginnings of what we see here. So let's say we're given point A, and of course point A in the Cartesian form, the xy ordered pair form, would end up being reflected as vector OA in terms of A's position, its head sort of relative to its tail anchored at the origin, which also could be thought of as, or designated as lowercase a. So that would be that vector there over 3 up 4. And so then if we have not only the sort of position vector of a point on the line, which is what we do have here, as well as some kind of vector that's actually called a direction vector that's parallel to the line, that's enough to do the actual construction. So what would the construction look like? Well, if you just designated some random point r on the line, and you wanted to talk about getting from O to R, so in other words, to describe r's position with the position vector OR, well, the way that you can get from O to R is, of course, going from O to A first, and then get yourself from A to R. So that's not a hard thing to do. So what's over here in terms of this triangular construct is that position vector OR, this red guy here, is equal to OA plus AR, which is a kind of a triangulation thing. Well, OR would be something that we can just designate like this, so these are equivalent. OA, we just saw over here, we're designating like that as sort of A. And then the new thing becomes, what is this AR piece? How do you move from A to R? Well, to move from A to R, we have the advantage of being able to use this guy here, because he is exactly parallel to this movement. And so if you thought about the length of that, and maybe even multiplied b by 2 to double its length, maybe that's roughly what it takes to get from that point to that point. So this AR entity, which has some t times b, t, you'll notice, is not a vector, it's a scalar, it's a single numerical value as it multiplies by the vector. And we saw in a previous podcast that that kind of multiplication of a vector by a number could maybe stretch it, shrink it, or maybe even reflect it if the number was negative. So this is the basic form for the vector equation of a line. It describes the position vector of any point on the line, any general point, the position vector of a specific known point on the line, and then some multiplier by some so-called direction vector that's actually parallel to the line. So let's bring it to life a bit more specifically. Let's find the vector equation of a line that has to pass through this point and be parallel, as it turns out, to this vector here. So in general, we want to use the form r is equal to a plus t times b. Well, r is referring to any general xy ordered pair because we're in two-dimensional space here, and we'll see that on the next slide. A, of course, if that's the point A in 2 space, then its position vector would be vector OA, which would look like that in vector form, plus apparently t times the direction vector that's parallel to the line in question. Well, we were just given that for free. So we're done, right? So we have a kind of a y is equal to mx plus b kind of a flavor to what's going on here, although it's just not as obvious in terms of how it looks in vector terms. Let's go here and say, well, okay, we just constructed this vector equation of a line where all of those x, y ordered pairs that were all along that line are equal to this, apparently. But what does it actually mean? So we could say 3 plus -1 times t, -2 plus 2 times t. So it looks like x is equal to 3 minus t. It looks like y is equal to -2 plus 2t. So what we can do here is we can solve for t in terms of x. That's right here. So if you just bring -t over and x over, t is equal to 3 minus x. And if you isolate t here in terms of y, you'll be adding this across. You've got y plus 2 divided by the 2. So t is equal to both this and this. And if they're both equal to t, then they're certainly equal to each other. And if you then say, okay, I've got this sort of xy thing going on here, double both sides, and then put this, the remaining piece into the y equals mx plus b form, you're here. So as it turns out, we've taken something that looks pretty abstract, namely the vector equation of a line, and we've actually represented it in its equivalent Cartesian equation form. So here it is, right? Here's the y is equal to -2x plus 4 line, and its relationship to its vector equation form would say, okay, firstly, to talk about any point on this line, that would mean any one of these xy sort of position vectors, to get from like the origin to maybe that point right there, what would you do? You would first get to the line itself, which is at 3, -2, right? That's what that's saying. And then work your way back to that point by taking this other direction vector and then maybe multiplying it by 5 or 6 to slide yourself all the way back to that point that we needed to get to. So what's going on here? Well, take a look at the scale here. Here's a scale of 1, and here's a scale over here of 2. Well, this -1, 2 is not sort of accidental. That would be saying for every -1 that you go this way, you go up 2. -1, up 2. So you've got this parallel thing, you've got a slope thing. It all hopefully works in terms of your understanding of the concept.